Test one. Okay, that's working. Okay, well, thank you everyone for being here, and welcome to our seminar speaker, Erika Jawin, today. So Erika, she's a research geologist working in planetary science at the Smithsonian Air and Space Museum in Washington, D.C. She got there right after her PhD at Brown University. That was in 2018. So Enrica is a very good example of what we can do with planetary science, because in planetary science, it's a huge topic and you can touch a lot of different kind of things in planetary science. And she's the perfect example of that. She's been working on the moon to determine the emplacement scenarios for volcanic deposits on the moon. She's been working on the surface response to climate variations in the Martian cryosphere as well. But today, she's going to present something completely different, right? Because we will have the pleasure to listen about the origins and the evolution of asteroid Bennu, if I pronounce this correctly, Bennu, okay, from the OSIRIS-REx mission. So, Erika, welcome again. Your turn.
Right, thank you. Is the mic good? All right, perfect. All right, so today we are going to talk about asteroids, the OSIRIS-REx mission that I worked on in my first job out of grad school as a postdoc, starting in 2018. And we'll talk all about my favorite asteroid, Bennu. So this is broken up into several parts. We'll see how many parts I can get through before we run out of time. Part one is an overview of the OSIRIS-REx mission, and I'll just comment that I was a postdoc on the mission. I will say I sometimes, but none of this could be done without the incredible efforts of the entire OSIRIS-REx team, scientists, engineers, navigation. Is pretty incredible. Okay, so from the very earliest perspective, what was OSIRIS-REx? What is Bennu? So OSIRIS-REx is NASA's first asteroid sample return mission ever. And this was a mission to the near-Earth asteroid Bennu. Bennu you can see spinning here. It's very beautiful. It is a low albedo asteroid. It's part of a spectral class that we called B types, which means that it is very dark. It seemed to contain high concentrations of organic materials, seemed to be highly aqueously altered. This is all from spectral data taken from Earth before the asteroid was even chosen as the target of the OSIRIS-REx mission. And these kinds of asteroids were thought to be linked to carbonaceous chondrites, a specific kind of meteorites that we have that are, again, dark, organic rich, and aqueously altered. And again, Bennu is a near-Earth asteroid, so keep that in mind. You can see on the right there that Bennu is about 500 meters in diameter. That can be kind of hard to visualize, so I took a lot of time and effort to try and give you a to-scale representation. So this is what Bennu would look like if it were coming a little bit too close. We'll see how the team would do in that situation. Maybe they'd still do pretty well against it. So OSIRIS-REx is, again, the name of the mission. It's a very long acronym. I'll say it once. It's Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer. All those words mean something specific about the goals and the objectives and the intention of the mission. I'll probably just call it OREX from here on out because it's a little bit of a mouthful. So the spacecraft was launched in 2016 on its way to the asteroid Bennu. I joined, very importantly, in 2018, about 2 or 3 months before we arrived at the asteroid. For 2-ish years, we orbited the asteroid, got a sense of its global geology, tried to get a sense of its evolution, critically all towards looking for a good and safe and scientifically interesting place on the asteroid to collect a sample so that we could bring that back to Earth. Our nominal sample collection was mid-2020. I don't know if you remember what you were doing in 2020. We were all locked home from COVID, so we had to push the sample collection date back a bunch of months to figure out how to do all of that remotely. We did collect the sample in October of 2020. The spacecraft stuck around for a little bit after that sample collection until the orbits were well suited to send the spacecraft back to Earth. That sample was in a sample return canister that detached from the spacecraft, made its way into Earth's atmosphere, and landed on Earth in, ooh, let me try the laser. Oh, my laser's not working, so I'll just use this. Landed on Earth in September of 2023. And so now the sample is on Earth. We're in the sample analysis phase of the mission. And so there are some really, really cool papers that have been coming out recently analyzing the OSIRIS-REx sample. And so on the left part of the slide here, you can see, oh, don't give away my joke. Don't give away my joke. Oh no. Okay, imagine you didn't just see that. This is the original logo for the mission. It's great. You can see the shape of the spacecraft, the solar panels, the sample collection instrument. The tag SAM is here at the end of the arm. I find this one boring. I prefer the original logo, which is this one here, which is sort of like the revenge aspect of the dinosaurs, getting one back to the asteroids. Unfortunately, this is not the official logo anymore. You can still find it on eBay if you want to buy it online. The OSIRIS-REx mission also won a Guinness World Record for the closest orbit of a planetary body ever. And Bennu also won a second Guinness World Record for being the smallest body ever orbited by a spacecraft. Way to go, Bennu. Okay, so that's kind of an overview of the mission, the setup. Again, the whole point of this mission was to collect a sample, bring it back to Earth. We did this using this tag SAM instrument, the touch and go sample acquisition mechanism, which is like a hubcap shaped mechanism here. It's about 30 centimeters in diameter. It would reach out, touch the surface of the asteroid, and then nitrogen gas was forced through the head into the subsurface, effectively fluidizing the regolith, near surface particles, pushing that upward into the sampler head. That nitrogen gas would exit through a mesh screen and the sample would be trapped within the sampler head. And then that arm would retract and it would deposit the sample head into the sample return canister in the belly of the spacecraft. That's this white little bathtub thing here. And then that return canister would detach from the spacecraft and come in through the atmosphere and land on Earth. The required sample mass set by the mission team was 60 grams of material. That's the minimum amount we needed to declare a successful mission. You know, Americans hate the metric system, so for comparison, 60 grams is about the weight of a full-grown hamster. Keep that in mind. So that was the plan. We were going to go collect a sample, find a nice smooth area on the surface, collect a sample, bring it back. That's not really what we encountered on the surface of the asteroid. That's a whole separate story. You can ask me about that later. But we did find a fantastic sample site. On October 20th, 2020, we touched the surface, made a huge mess, blasted rocks into the air, particles, dust flying everywhere. And the sample came back, landed on Earth. We opened up the sample return canister, and turned out we collected over twice the required mass, 120 grams, 121.6 grams of material, 2 hamsters, in fact. And the samples are really just beginning to be analyzed by the sample analysis team. They're so cool. It gets into a lot of geochemistry that I don't understand. I just like to look at pictures of rocks. But the papers there's a few papers that were just published a week or so ago. They're so cool, so you gotta check them out. Okay, on to part 2. Where did Bennu come from? Where did the asteroid Bennu come from? And what was its evolutionary path? So Bennu is what we call a rubble pile asteroid. This means that there was an original parent body. We believe it was about 100 kilometers in diameter, so similar to the size of Ceres, that was disrupted, potentially catastrophically fragmented, blasted apart, like you can see in this simulation on the right. And then individual fragments of this parent body came back together just under the force of their own gravity of those constituent particles and formed a new secondary body. And critically, those fragments are formed of the parent body, but they're forming a new asteroid. So we'll talk about Bennu the asteroid, which in a sense is distinct from Bennu the parent body, but they're intimately connected. So we think that that Bennu formed, that this disruption occurred Well, we think the disruption occurred probably 65 million to a billion years ago. When Bennu formed is a little bit more nuanced, that again, if you're curious, feel free to ask about. I'll also note that it's when you have one of these catastrophic impacts of a parent body, you do not form one rubble pile from one parent body. When you have these kinds of impacts, you can form tens of thousands of these rubble pile asteroids, and you can form what's called an asteroid family. Objects that are distinct bodies but have similar orbits that are all set by the original orbit of the parent body and altered by that impact that happened. So Bennu could be one of a huge number of similar objects formed in this kind of impact. So Bennu itself, as I said, we believed it was a rubble pile asteroid. So what does that mean from a geological perspective? Rubble piles, again, are piles of individual boulders. They're only loosely held together by the gravity of the particles. So these objects are generally very weak, have a low degree of strength within the interior. Often they're non-spherical. They can be these sort of diamond-shaped asteroids with equatorial bulges or ridges. Because they're made of boulders, they tend to have very rugged surfaces with potentially huge boulders relative to the size of the body. The surfaces are unconsolidated because it's just gravel, basically. And quantitatively, they tend to have things like low density, high porosity, and low slopes, again, because there's very little strength in the interior of these asteroids. And so I mentioned that these are basically made of boulders. And I also mentioned that sample collection for the mission, we expected to go and find a nice, easy place to sample from. We expected there to be certain regions on Bennu that were smooth, made of fine-grained materials. The phrase smooth sandy beaches were used by the team to try and find a sample selection location. We got to Bennu and started taking pictures of its surface. And we said, oh no, it's just boulders everywhere. The surface is incredibly rugged. It's just boulders on tops of boulders. There's boulders of different size and shapes and sticking out of the ground and buried by other boulders. So it was a total scramble to try and find a safe place to sample. But from a scientific perspective, this is actually fantastic because every boulder that you see here is a fragment of the parent body from somewhere on it or in it. And in it is also critical because when you go and explore other planets, you're generally restricted to looking at the surfaces of these bodies. And so there's a huge amount of research, including things like radar that I love and that a lot of you work on here to try and probe the subsurface properties of planetary bodies. But by looking at rubble piles, if you've effectively blown up the parent body, you can look at its interior directly. And so looking at the boulders showed us that there's a actually kind of huge range of morphological and other properties of these boulders. They ranged in albedo, in morphology, so in their sort of texture and appearance, their thermophysical properties. Some boulders are rugged, some are smooth, there's layering in some, there's individual clasts in others. There's a huge amount of variety here. So this allows us to enable some characterization of the parent body that we wouldn't be able to do if it were still a single parent body. And this is what I'm going to spend the majority of the second half of this talk discussing. But there's a little bit more context before then. So Bennu, rubble pile, formed, I said it's a near-Earth asteroid, but Bennu didn't start out as a near-Earth asteroid. So how did it form and where did it get to where it currently is? So we believe that Bennu formed in the inner part of the main asteroid belt. So most asteroids in the solar system are in the main belt, which is located between the orbits of Mars and Jupiter. So that's all of these little dots here. Bennu probably formed in the asteroid belt, although there's some really cool new data that was just published last week or so looking at the Bennu sample that suggests that the parent body may have formed much farther out in the solar system, like beyond the orbit of Saturn. So much, much farther than is even shown in this figure here. But then that parent body migrated eventually into the asteroid belt and then was fragmented, blasted apart. And that's where Bennu, the asteroid, was probably born. But that's not where Bennu is currently located. Bennu's current orbit, as I said, is a near-Earth asteroid, which just means that its orbit is near the Earth. So Bennu is the green circle here. Its orbit is generally between Mars and Earth. It does cross Earth's orbit a couple times, which makes it a hazardous, potentially hazardous asteroid, which is another motivation to study it and see how its orbit evolved. And so how did Bennu become a near-Earth asteroid? How did it get from out beyond Mars to now crossing Earth's orbit? And that's because of this cool non-gravitational force called the Yarkovsky effect. Does anyone here, this is like a super asteroid thing. Has anyone here heard of the Yarkovsky effect? Couple hands, yeah. So this is basically a thermal radiation force that affects small non-spherical bodies like small asteroids. So the concept is that you have a rotating body that's non-spherical. So the day side part of the asteroid that's illuminated by the sun heats up. And then as the asteroid rotates, it radiates this heat away. So that thermal radiation effectively gives it a little bit of a push, a torque almost. And so over enough rotations and a long enough period of time, you can actually deflect the entire asteroid's orbit, either inwards or outwards, depending on its rotation and its overall shape. So Bennu was hanging out in the asteroid belt, but because it's not perfectly spherical and very small, this Yarkovsky effect pushed it just a little bit towards the sun so that it eventually migrated in towards the inner solar system. And there's a little bit more to that. There's things called Kirkwood gaps in the asteroid belt and mean motion resonances of gravitational forces of planets pulling on each other. For now, Yarkovsky is like the main thing that you can think about. And so that force basically ejected Bennu out of the main belt towards NEA space. And there was a very cool paper done by a colleague of mine, Ron Baluz, that looked at individual boulders on Bennu and counted basically micro craters, these very, very small craters on individual boulders on Bennu, and did basically crater counting to show that Bennu probably has been in near-Earth space for less than 2 million years. So Bennu has only been in NEA for about 1.75 million years, which is super, super quick on planetary timescales. You're all probably mostly geologists, so that's not crazy to you. But 2 million years is like the blink of an eye. Okay, so that gets us Bennu, its origins, how it got to be a near-Earth asteroid. I'm now going to go into some work that I have been working on for the last couple of years, looking in a little bit more detail about its boulders. So there's like the silly title, Why Bennu's Boulders Are Its Best Fits. So I mentioned that there was basically a diversity of boulders that we found on the asteroid when the spacecraft was collecting all these data about the asteroid. So what we found, first of all, was that there seemed to be two populations of boulders that we could separate based on their brightness, their overall reflectance. And so that's shown in what's called a size frequency distribution plot here. On the x-axis, you have the boulder size, and on the y-axis, you have the frequency, how common those boulders are. So there are more small boulders than large boulders. It's the first thing to know. The second thing is that there's two different curves here with different slopes. The dark blue dots are the one population of boulders that have a certain slope, and then the light blue dots are a apparently separate population of brighter boulders that have a different distribution. So this suggests that there's two different populations of boulders on Bennu. This histogram is shown on the right-hand side, showing you that with respect to reflectance, again, there's two distributions here of darker boulders and brighter boulders. So I'll call them dark boulders and bright boulders. But the huge thing to keep in mind here is that if you look at the normal reflectance values, the brightness, the difference in reflectance is like 4.5 reflectance to 6.5 reflectance. And the reflectance of coal is this blue dashed line. So everything is super dark. And the difference between the dark and the bright boulders is like that, right? So I'm going to show you pictures of these boulders that look super different, but they look different because the cameras were specifically designed on the spacecraft to image very, very dark objects. And I also stretched the you know what out of these images to make it really highlight those differences. But those caveats aside, we do see these dark boulders and these bright boulders, and it's not just a difference in reflectance, it's a difference in texture as well, where the darker boulders are very rugged. They have this clastic texture, so individual clasts in a matrix, where the brighter boulders are much smoother and more angular. And these two populations also seem to propagate into other properties like thermophysical data. So this table in the lower right is showing various properties like thermal inertia, thermal conductivity, porosity, and tensile strength that we got from our thermal emission spectrometer instrument. And those values are also different between the dark boulders and the bright boulders. So there's these morphological and physical variations apparently between the two groups. There also seemed to be potentially a spectral difference where certain bright boulders on the asteroid had these distinct bright spots on them. So bright boulders hosting even brighter exposures. And these boulders were spatially correlated with spectral absorption that indicated the presence of carbonates, which is formed in aqueous alteration environments. And now Bennu, as we mentioned at the beginning, is a B-type asteroid, meaning its parent body, the original body, was extensively altered by water. Aqueous alteration seemed to be ubiquitous on the entire body. And that's shown in the initial spectral data that we collected of the asteroid, showing it's similar to Ci and Cm chondrites, these aqueously altered meteorites. But these specific boulders with bright spots also have this presence of carbonate. So maybe these were even more aqueously altered than the rest of Bennu. So we're seeing this diversity amongst the boulder populations. And so what we did is we started to develop this taxonomy for boulders, where we had, again, dark boulders and bright boulders. But within those populations, we started to find more morphologic diversity, where within the dark boulders, some of them were more rugged and clastic. Some of them were a bit smoother with this sort of crackly, we call it elephant skin-like texture. And then in the bright boulders, there are those that are more smooth and more angular, and some that had these bright spots. So we had developed this taxonomy and wanted to be a little bit more rigorous about this. And so what we did is we looked at all of the boulders over a threshold of like 2 meters near the sample collection site where we had great high resolution data. And we wanted to analyze them in some sort of rigorous, comparable way between boulders. And so the plan that I came up with was to develop a series of qualitative labels that we could assign to each boulder describing its morphology. And so you basically establish a bunch of categories. These seem like the main things that were different between the boulders. Is it angular or rounded or in the middle? Is the texture rough or smooth? Are there clasts or not? Are there layers or bright spots or not? And we would analyze all of these boulders in this one concentrated area, assign a label to each one, and then apply some sort of automated clustering algorithm to sort them into groups and see if we could reproduce this type A, B, C, D category that we thought was present or not. So, I'll just take a moment for a quick aside here that I developed. I thought this was like so great that I made up this methodology to do this. And I was talking to my husband, who is a sociologist, and he told me, he said, "Oh, it sounds like you're doing coding." And I was like, no, I'm like, it's not writing any code. I'm just gonna assign these labels manually. And he's like, no, it sounds like you're doing coding. And I was like, no, man, I just told you, I'm not writing any software yet. That's the next step. And he's like, you never listen to me. And I was like, you never listen to me. And he's like, no, we don't have to talk about that. But he's like, no, listen. In qualitative research methods, there is a very well-established practice called coding, where you take some sort of qualitative data and separate it into categories and assign labels so that you can compare those qualitative properties. So yeah, it turns out I was super doing coding. And this is a very, very well-established methodology. And so I realized that quickly, and then looked up some very basic qualitative research model literature. This This Saldana reference here, this is the latest edition of a handbook in qualitative research methods, has been cited 90,000 times, 90,000. So is anyone in here, there's probably some students, are any of you sociologists or taken any humanities or social science courses? Okay, do that. This is like a teachable moment thing where don't assume that the things that we learn in only our courses are the things we should apply to our research. There is incredibly valuable research methods everywhere. So keep an open eye, keep an ear out, take courses in other things, because I would have saved so much time if I had looked at this textbook at any time during this whole process, and I could have probably done a more rigorous analysis from the beginning. So yeah, qualitative research methods are super important. Also, part of the 90,000 references things is because this is super applicable for machine learning and AI applications now, which is sort of our next plan for this. But trying to figure out how to quantize or at least categorize qualitative data, super important. So yeah, that's teachable moment. And so we did this for like 400-ish boulders near where we collected our sample site from. We got a bunch of quantitative data, albedo, thermophysical properties, roughness, and applied a series of labels to each boulder. And then what I did next is apply a couple of clustering algorithms. So k-means is a very, very, very common clustering algorithm. Has anyone used k-means before? Basically, you take a bunch of data, you figure out a centroid, calculate a mean value, that centroid, and cluster based on which mean you're closest to. Okay, that works great for albedo, for roughness, for quantitative data. But for categorical or qualitative data, you can't find the mean of a bunch of letters, but you can find the mode of a bunch of letters. So there is a clustering algorithm called k-modes that was developed for exactly this purpose. And so we applied that k-modes clustering algorithms. Again, very foundational clustering routine in machine learning algorithms. So super, super relevant. And we applied this clustering algorithm on our boulder data and basically said, hey, sort this into whatever number of groups you think is appropriate. And it very nicely recreated our type A, B, C, D clustering with a little bit of stray data, but you kind of expect that from any sort of automated routine. So we took this as evidence supporting our type A, B, C, D categorization, which is great. So then the next step is you can then combine your quantitative and qualitative data, your k-means and k-modes simultaneously, and cluster albedo data and morphology data simultaneously using this routine called k-prototypes. And so we did that. We said, okay, take all the data that we have and do the same thing, cluster all the data you think in the best way. And it did recreate our type ABCD distribution very nicely. Again, there's dark boulders and bright boulders, which are the type AB are the dark and CD are the bright boulders. And then there's a few that seem to have like a half and half boulder, which we'll talk about in a second. And so then we compared our manual classification against the clustering results, and it had very, very low mismatches between the two. So we are saying, okay, great, we're going to assume that the type A through D clustering is real enough. There's dark boulders and bright boulders and some variability within there. So what does that actually mean for boulders on Bennu and its evolution and its parent body? Well, if we take our 4 boulder groups, again, A and B are darker, lower thermal inertia, higher porosity. The type C and D boulders are brighter, higher thermal inertia, lower porosity, maybe these bright spots that indicate more aqueous alteration. We can start to look at their distribution and their spatial associations to try and determine something about the origin and the evolution of Bennu. For example, did these boulders even come from the same parent body, or are these just random boulders from different asteroids? So when we started looking through the images and the associations between boulders, yes, we have these 4 groups, but as I mentioned, we have a lot of boulders that seem to be like a half and half. You have a boulder that has a portion of it that's totally consistent with a type A, but then a separate portion that looks more consistent with a type B in distinct layers. There's other boulders that again seem like a type A in certain areas and a type B in others, but it looks like the type B is maybe a rind or a coating on the exterior of a type A boulder that's just being eroded off through time. So from these types of associations, we can say that type A and B boulders probably formed in proximity on a single parent body. And due to the clastic layered texture of these type A boulders, it's possible that these represent impact breccias. And so those boulders would have had to form at or near the surface of the parent body in order to be fragmented and then cemented back into a competent boulder. So, okay, type A and B boulders formed on one parent body near the surface, based only on stratigraphy and physical contacts between these boulders. What about the other ones, the C and D? So much less common, but we did find similar relationships between the type C and D boulders, where there seems to be a small portion of potentially like a rind or an outer layer of a type C boulder on an otherwise slightly rougher boulder with these bright spots. So we call these type C and D boulders. These are all much smaller than the ABs, but similarly, we can use these spatial contacts to say that C and D boulders formed in proximity on their own parent body. These boulders don't have clasts, they have higher thermal inertia, lower porosity, so they probably formed beneath the outer portion of the asteroid where impacts dominated. Also, because these bright spots that are potentially indicative of carbonates are in these boulders, maybe they had experienced a more extensive aqueous alteration to form these carbonates that did not exist in the outer regions towards the surface. So, okay, so we have our AB boulders on one body. We have our CD boulders on one body. Were those two bodies the same or are these separate asteroids? What we would love to see is a type A boulder with a type C or a D, or maybe a type D boulder with a type B, some sort of relationship between those two. And actually, if you look at the type A boulders, these rugged clastic boulders, we do see fragments of what look like type C or D bright angular boulders as individual clasts within these type A boulders. So this is what we were looking for. And this is evidence that suggests that all four of these boulder types were present on a single parent body prior to its disruption. One parent body. So keeping that in mind, what can we then predict about the parent body from these type A, B, C, D boulders? The outer portion was dominated by impacts. The interior experienced more extended period of aqueous alteration. And then probably, because it's a planetary object, we know there probably were impacts on it. Some of those could have excavated that deeper type CD material, deposited it on the surface to then become lithified into some of those superficial type A boulders. All from simple stratigraphic morphologic analyses. That's kind of cool, right? You can do all that just from looking at pictures. I think it's pretty cool. Okay, so that is basically the summary of this lovely paper that we published a year or so ago. We're trying to take some more enhanced machine learning approaches to these data that we've done all this effort coding and extracting, and I don't have anything to present yet, but that's sort of the next step of that research. So with the little bit of time left, I want to talk about the return sample. Caveat, I am not a sample analysis person. I think Romy Hanna is online. So if you have sample questions, ask her. You can ask me, but I might just ask her. Okay. September 24th, 2023 was a very stressful day. It was when the sample landed on Earth. It was mostly nominal, except that there was this first initial parachute called a drogue parachute that was supposed to deploy to slow the whole thing down before the main parachute deployed. The drogue never deployed. So the cameras didn't know where to point to like give us this great view of it landing. And so it was kind of just like, oh, there's no news, there's no news. Oh, there it is on the ground. So it was kind of like a jump scare. Oh, it landed. Turns out it was totally fine. It didn't crash. It was pristine. It landed right side up. It didn't bounce. It was great. The sample was whisked very quickly to Johnson Space Center, to their curation facility. It was very hard to get the sample return canister open, but eventually they got it open. And to me, the coolest part, well, the first cool part of all of this so far was when we started looking at what the sample looked like. So this image on the left is Bennu taken from orbit. This boulder here is about the size of a horse. Okay, no, longhorn. It's like the size of a longhorn, okay? This image on the right is taken of the sample, if you note the scale bars, and yet the morphology of these two is strikingly similar, which we're totally not expecting at all. In fact, it seems like there is morphologic diversity within the sample that includes we call it a hummocky, sort of rugged, rounded particle group. There's another one that's more smooth and angular. And then there's another one that has these sort of brighter spots on it. Does that sound familiar? Have I said those words enough to you that it seems like there could be a connection between the hummocky particles and maybe an origin from these type A boulders, whereas the angular particles could have originated from the type C particles. So this is suggesting that Bennu materials could follow fractal behaviors across orders of magnitude, which I don't know what that means yet. It just is very unexpected and is really cool, and is actively being looked into by the team. Stay tuned. Maybe that means nothing. Maybe that's something really incredibly important. I'm just not really sure yet, but I think it's very, very cool. What's maybe a little bit of more broad appeal is some of the actual science results coming out by the team. One that was led by my former postdoc advisor, Tim McCoy, is so wild that through analyzing these samples, people from like 50 or 100 different labs across the Earth found different salts within the samples, including sodium phosphates, sodium-rich carbonates, specifically trona, sulfates, chlorides, fluorides. And when you put all of these salts together, you can basically form a single evaporitic sequence that was happening within Bennu's parent body, again, ancient parent body, that indicates that on the parent body, there was this warm, probably, salty, water-rich environment that slowly was drying out through time. So this warm, salty environment that you could call habitable environment was present on Bennu's parent body. A separate paper came out at the same time showing that the sample contained this huge diversity of organic material that we consider to be building blocks of life. 14 of 20 amino acids that are present in terrestrial biology. All 5 nucleobases were present in the sample. Bioessential sugars were found in this sample. Like this huge diversity of things that we think are essential for life to form were present. But it's not just that they were present, it's that they were present in a habitable environment. So this is a big deal because, in my opinion, this is really special because this expands what we think of as habitable environments in the solar system in space and time. It's not just Earth, it's not just Mars, it's not just the icy satellites of the outer solar system. Habitable environments with prebiotic compounds could have been present within a few million years of the solar system forming. And carbonaceous asteroids like Bennu, or Bennu's parent body, we know littered the solar system, were basically impacted and blasted and deposited their materials across the surfaces of all the inner planets, the icy moons of the outer solar system. So these either building blocks of life or potentially emergent life could have been deposited onto like everything in the solar system. So thinking about the emergence of life, the pathways have opened up immensely, which is, again, so cool, which is wild. Okay, do I have time for this last part? I'll be very brief. I think I have like 2 or 3 more minutes. Okay. So the sample of Bennu is on Earth. The sample return canister detached from the spacecraft, came in through the atmosphere, landed on the surface. The spacecraft is still up there. So you could go and just crash it into the sun to get rid of it, Or you take the billion-dollar spacecraft and you send it to something else to go and get even more essentially free science out of it. So what we did is basically put the OSIRIS-REx spacecraft under a rebrand. We are now on our way to a new asteroid called Apophis. So OSIRIS-REx is officially a new mission called the OSIRIS Apophis Explorer, or OSIRIS-APEX. And APEX is going to visit asteroid Apophis because it will be coming very close to Earth in April 2029, April 13th, which is a Friday, Friday the 13th. Apophis will be coming insanely close to Earth. So this is smaller than Bennu, 340 meters in diameter. It will be coming close to Earth within the orbit of geosynchronous satellites. So 32,000 kilometers. Like you'll be able to see Apophis with the naked eye on about half of the planet, Europe and Africa. So this is going to be a global event. 2029 has already been proposed as the International Year of Planetary Defense and Asteroid Awareness in recognition of this event. So there will be at least one spacecraft going to Apophis around this event to observe what happens. Specifically, APEX is going to be rendezvousing with Apophis immediately after that close approach to determine how the surface geology and the orbit of the asteroid responds to this close approach. Is that gravitational forcing going to shake surface material loose and cause a bunch of landslides? Is it going to change how the orbit is tumbling? Is it going to rip the whole asteroid apart? No, but those kinds of questions. And then the culmination of this will be what we're calling a STIR maneuver, spacecraft thruster interaction with regolith, where the spacecraft will descend, the spacecraft will descend close to the surface and turn on its thrusters and basically blow a big hole in the surface of the asteroid to learn about things like space weathering, to quantify the geotechnical properties of the regolith, to try and find evidence of near surface layering. This is critical for science questions, but also really, really important for planetary defense applications to know how the surface of a small asteroid responds to some kind of external forcing. So stay tuned, 2029, you will be hearing about this in the future. It will be all over the news. Okay, so that is pretty much it. A couple of takeaways: that the OSIRIS-REx mission investigated Bennu, this weird little rubble pile that's covered in boulders. It is boulders, that's all it is, basically. From our analysis, we argue that there probably was a single yet heterogeneous parent body that was widely sampled to form Bennu as we see it today. And this heterogeneity indicates variable roles of aqueous alteration in the interior and impacts towards the exterior. And the return sample seems to reflect this wide variation in parent body processes that we find at the boulder scale. And stay tuned for Apophis in 2029. Thank you.
Thank you, excellent, Erika. And just in time for our sequence of 15 minutes of questions. Any questions in the room? Sure.
Good catch.
This thing. Okay. I guess I have two quick questions. The first one being, now that you've looked at Bennu and sort of characterized its, surface features, have you seen any other evidence for like other objects that came from the same parent body?
Ooh,
close by or otherwise?
Yeah. So what I didn't talk at all about here is that while NASA was sending OSIRIS-REx to Bennu, the Japanese space agency JAXA sent a mission called Hayabusa 2 to a similar asteroid called Ryugu. And Ryugu is very similar to Bennu in a lot of ways. It's kind of different in other ways. And the question this whole time has been, did these two asteroids come from the same or a similar parent body? And it's been kind of an open question this whole time. There's some things that really argue towards maybe a very similar parent body. There's some things, especially in the sample analysis, that's emerging that suggests maybe they were separate bodies. But I think there's basically consensus that Bennu and Ryugu must have originated from at least a similar kind of parent body that maybe formed from a similar reservoir of materials. And whether it was the same exact parent body, I don't think that there's enough evidence to definitely say yes or no yet, but they were very similar.
And my second question kind of builds off that. You kind of said like a size estimate for the parent body. How do you figure that out?
Ooh, so another great question. So the main thing is that these kinds of carbonaceous asteroids are very primitive. So they never differentiated, which means that it never got hot enough from being massive enough and overburden pressure to melt the body completely so that you segregate the heavy elements like metal into the interior of the body to form a core, which then would separate the more lighter, like rocky materials towards the outside. That process never happened with these kinds of objects. So that gives you a very firm upper limit on the size of the parent body. We kind of assume 100-kilometer-ish diameter, Ceres-ish, because that is the general size of planetesimals, like baby planets, basically. But more than that, that has not been constrained any further than that from the sample analysis. But that kind of thing is exactly what the sample people are looking for.
In geology, boulder is a particular size designation, but what you're calling boulders, it strikes me, are a lot of different sizes. What's the cement for the boulders? Is it the carbonates that you're measuring, or is it something else?
Well, the first part, got to call out the Wentworth scale. We had a lot of conversations about boulders versus cobbles versus pebbles. So the boulders here that I'm referring to are all boulders in that they're over like 30 centimeters-ish. The cement, the matrix that we're seeing here, we have been assuming is similar to the matrix in some of the carbonaceous meteorites that we bring back. So it's kind of this like sludgy mixture of hydrated clays, a lot of serpentines and other sorts of hydrated phyllosilicates. There's all kinds of stuff mixed into that matrix. A lot of it's very amorphous, but it seems to be dominated by hydrated clays.
And there are a lot of fragments that are smaller than what you're calling boulders, all the way down. So I mean, that I was thinking fractal the whole time before you mentioned it. And so what I don't have a sense for, you have a parent body that hits something else and atomizes. It probably hits at high speed. And how long does it take this Bennu to form? Because it might be forming from very, very small particles that are all agglutinated in a fractal way to all kinds of size classes that you still see on the surface.
Well, okay, so what's interesting is that there is really no evidence for extensive shock or melting in these materials. So it's not necessarily blasting apart and melting like we think of in impacts on the moon or planet scale, where you get a lot of impact melt. But yes, it's definitely creating a huge size range of particles. You also, of course, have Bennu and Bennu onwards evolution and grinding of particles. So and impact. So you'll continue to evolve the boulder distribution even after the rubble pile forms. But not to be weaselly about your question about how long does it take for a rubble pile to form, but some really cool research came out recently suggesting that Bennu might not be a first generation rubble pile. It could be what we call an nth generation rubble pile, where you have your initial impact that forms. You form a rubble pile from the bits, but then another impact comes in, blasts Bennu apart, and then you have that reforming a new Bennu made from Bennu bits, but it's technically a new body because it was blasted apart and came back together. Maybe you have two rubble piles that combine and you're mixing all the stuff. So the age of a individual rubble pile is very, very uncertain. And coupled with that is the way that we generally assign dates to planetary surfaces is through crater counting. And because rubble pile surfaces are so weak, the craters that form seem to form in sizes that are different than craters you would form on a much larger body like the moon. So the way that you connect a distribution of crater sizes to its age could be completely different than our understanding for planetary bodies. So there's pretty big error bars on a lot of this. Good aim, yeah.
So you had mentioned that it could be an nth body, or an nth generation, like rubble pile.
Yeah.
If there's no evidence of shock, how could it be completely disassociated and then reaccumulate?
That's a good question. There's almost no strength in the interior of these bodies. It's boulders all the way down. The macro porosity could be 40%. If you have a big enough impact, it could just blast everything apart without necessarily melting anything. That's my general sense. I'm not really an impacts guy, but
I mean,
we
You would have
do
melting. Yeah.
we do see craters on Bennu of
Okay.
all different sizes, from maybe 100 or 100 plus meters down to individual craters on boulders. And there's some evidence, I think it's been published, for micro craters on some of the sample. So I think you do see a little bit of melting at like the pit scale, but
Okay.
we don't see any melt ponds or anything like that. Definitely not.
That actually leads to my second question, which is based off of your albedo distinguishing or using that to distinguish between those two different colors.
Mhm.
How would space weathering affect that? Because it's going to cause spectral darkening of everything.
Aha, or does it? So yes,
Yeah.
yes.
I mean, that's one of the big reasons why we did this.
Yeah. So canonically, the thought is that like on the moon, space weathering darkens and reddens.
Mhm.
On carbonaceous bodies, it seems like you can actually brighten and blue in. More blue it.
Yeah.
But what's wild is Bennu and Ryugu, similar asteroids, not exactly the same spectral type, but similar. It seems like there was a reddening and bluing in opposite directions, and it's pretty unclear. What we see on Bennu, that I can say with more confidence, is that we see an association between small, apparently fresh craters and darker, redder material exposed inside those craters. So on Bennu, it seems like as you evolve, you brighten and blueing. It's still super dark. So space weathering is not space weathering is not space weathering. It's very complicated. Yep.
Thank you.
Yeah.
We have a question online, maybe first. Ron?
Yeah, I'm here. Yeah, this is Romy Hannah. Hi, Eric.
Hi, Romy. Hi, Romy.
That was great. Okay, so I agree that the AB boulders look like impact breccias to me. But what do you think of Ishimaru and Loretta's paper talking about how some of those layered boulders could have formed from settling deposition in water? I've been trying to figure out if the layering could be from impact versus that thing that they propose. I was wondering if you had any thoughts on that.
Yeah, so actually this image that's on the screen right now is a good example. So I was saying that we see layering in the boulders, like you can see here, there's, it doesn't show up maybe that well, but there's layering within the type A parts of this boulder, and then within the type B exposures, there's also some fine layering as well. So we argue that this could be evidence of impact breccias. You see similar sorts of layering on Ryugu as well. They also argue for impact brecciation originating layering. There's another paper from Kana Ishimaru at Arizona saying that maybe this layering is more of a sediment deposition feature as material sort of settles out. Just give me some context, Romy. So I think that's very cool, but I have a harder time seeing how you can get extensive bedding on a parent body near, well, interior in this sort of sequence. You'd need to have a lot of flowing water at different flow rates that you're switching between, like more rapid flow rate to move these large clasts. These clasts can be up to 1 meter or 2 meters in diameter. And then you would rapidly decrease the flow rate and get this very fine-grained, like sub-resolution particle size deposition, and then go back up again with the flow rate. It just demands a much more complicated hydrological system that I don't have as good of a sense for. I'm not saying it didn't happen, I just don't, I can't visualize the process as much.
Okay, excellent. Thank you.
Yeah.
A question, Chris?
This was a really cool talk. Thanks.
Thank you.
You mentioned earlier, we talked about the asteroid has only been in a near Earth orbit for about 2 million years.
Yeah.
That was surprising. How long did asteroids typically stay in a near Earth orbit, or is this their only data point?
No. So near Earth asteroids are all transient. They pretty much all come from the main belt and are just passing through near Earth space until they hit a planet or crash into the sun or get ejected out of the solar system. So they're all transient. And the time that they stay in NEA space is generally in the millions, maybe a couple 100 million years, but no more than that, because you're getting the gravitational torques from all the other planets. Because they're on unstable orbits, they're not super circular, so they do have these close approaches with other planets, just like Apophis. And so that leads to that short lifetime. They're just going to hit something or get ejected out somewhere else.
Actually, we have a remote question from Kurt Tallstrup about the return sample. This is a two-parter.
Uh-oh.
Have any of the sample particles shown glass?
Ooh. So there probably are some amorphous phases. There's some amorphous phases within the sample, I believe, but that's not really glass. As far as I know, there's no quenched glass that was found. When I hear glass, I always think of like volcanic explosive quenched glass. Definitely none of that. I would say the closest thing would probably be some kind of amorphous phase, but that's getting a little bit beyond my expertise area. So I might just point you to a paper that just came out last-ish week, Zega and McCoy, that was in Nature Geoscience. They talked a lot about the sample analysis, so definitely check that out.
Okay. Romy has chimed in indicating that no glass has yet been observed.
Thanks, Romy.
And the second part of the question is, are there any particles of metal that have been detected?
Oh, sure. There are some iron nickel sulfides, I believe. So those are pretty common in the carbonaceous meteorites. Not like metal, like Psyche, big fragments, but there's definitely small like sulfide, like metal blebs that are present in these kinds of meteorites. And Romy, correct me if I'm wrong, but I'm pretty sure those have been found. But she'll have the final word on that.
All right, thanks for the great talk. If Bennu impacted Earth, would it disassemble into all boulders, or would it maintain a coherence and really be a danger?
So that is a great question, and Sean and I were talking about that this morning. Again, not an impact guy. I don't do a ton of planetary defense stuff, but it seems like since there's such a small degree of strength in the interior of these bodies, there's nothing holding them together other than their gravity. At the equator of Bennu, the escape velocity is basically 0. So it doesn't take a lot of energy to loft particles off the surface. The surface strength is basically none. So like if you tried to stand on the surface, it would be like standing on popcorn. You would just kind of sink through. So my sense is that it would break up well before it actually made it to the surface into its constituent parts. So then your next question obviously will be, what's the largest individual fragment within these rubble piles? And that we really don't know.
Question.
Yeah, great question. So I think that your actual threat is going to depend on the largest fragment in these kinds of bodies. So Bennu's 500 meters diameter. We know there is one coherent boulder that is 100 meters in diameter. That's what's exposed at the surface. It could be bigger in the subsurface, but it probably is not the whole interior of Bennu. So maybe a couple 100 meters in diameter. That's very different from a 500-meter competent body, right?
Right. I think the last question was actually trying to address the end of the world, but it might not be it, right? Okay, so right in time, and thank you again, Erika. So there is the student lunch, co-coordinated by Mercedes and Vincent here, so you can get to them. Where is the meeting time? Where do you want to meet? In the lobby at noon? Or yes, okay, at noon. And we still have some slots after 3:30. I think if you want to meet with Erika, it can be remote. In that case, you can tell me if you are on the main campus, and I will get you a Zoom link. And we will have a dinner also tonight at Hop Dodi, not far from here. So if you want to come and discuss with Erika around a burger, just let me know, and we will organize that. And that's it. Thank you.